My name is Holden Mays, and this is my video lab report for Lab 5 for Physics 2212 at Georgia Tech. This report will cover the lab in 4 sections, starting with an introduction to the lab and the physics principles most relevant to the lab, the measurements acquired experimentally during the lab, an overview of the computational model designed for this lab, and finishing off with a couple of discussion questions. The goal of this lab was to witness Faraday's law in action by comparing the time required for a bar magnet dropped through an aluminum tube to exit the tube to the time required for a free-falling magnet to fall the same distance. When a bar magnet is dropped through an aluminum tube, the bar magnet's magnetic field changes relative to the tube. The magnetic field experienced at any given point on the tube varies as the magnet falls. This changing magnetic field creates an induced current in the aluminum tube, which creates its own magnetic field that causes a magnetic force to act on the falling bar magnet that opposes the bar magnet's velocity. As gravity accelerates the bar magnet down the aluminum tube will exert a magnetic force on the bar magnet that opposes gravity. Eventually, this magnetic force will be equal in magnitude to the force due to gravity, causing the bar magnet to fall at a constant velocity. The laws most relevant to this lab are the Barrot-Savart law, which is used to find the magnetic field vector at any given position caused by a single source, Faraday's law, which states that a magnetic flux that changes over time results in a Curly electric field and thus an EMF, and Lenz's law, which states that the resulting magnetic field will oppose the change in flux. These are the values found experimentally during the lab. Aluminum width refers to the width of the layers of aluminum surrounding the cardboard tube, while inner radius refers to the radius of the cardboard tube itself. The value of mu used for the computational model was found during Lab 3. The magnet took an average of 2.35 seconds to fall through the tube, compared to the 0.25 seconds it takes to fall the same distance in free fall when dropped from rest. The computational model is animated, and so it is best viewed by running the model yourself. I recommend clicking on the link in the description to better examine the model. The gray cylinder in the model represents the hollow aluminum tube and is actually a tall stack of identical rings. These rings gain color as the magnet falls near them, blue coloration representing a clockwise induced current as viewed from above, and red coloration referring to a counterclockwise induced current. The intensity of the color indicates the relative magnitude of the induced current, with intense colors indicating stronger currents. The excerpts from the computational model's code depicted here calculate the magnetic field of the bar magnet and the change in flux over the change in time at a ring in the tube, respectively. The code depicted here calculates the current flowing through any individual ring of aluminum based on the change in flux, and colors that ring based on current direction and magnitude. The magnetic field at any ring is then used to calculate the total magnetic force acting on the magnet using Newton's third law, as the magnetic force acting on the tube is equal in magnitude to the magnetic force by the tube acting on the magnet. The net force acting on the magnet and the magnet's velocity and position vector are then updated. The induced current in the aluminum tube is equal to the EMF caused by the falling magnet divided by the resistivity of the aluminum foil. A resistivity close to 0 would result in a very strong induced current in the aluminum foil, which would result in a larger magnetic force acting on the magnet. The magnet would fall at a constant velocity much smaller than with a comparatively higher resistivity. If holes or slots were cut into the aluminum tube, there would be no induced current through the aluminum tube in sections level with the cuts, resulting in much less magnetic force acting on the magnet when it is level with a cut, causing the magnet to exit the tube faster.